Alright, gang, here we go. This is Chem 1, Unit 8, Part 3. We're talking about limiting reactants. Alright, so let's take a break from chemistry real quick. And let's just pretend for a second that we are running a restaurant. And in our restaurant, we are going to sell turkey sandwiches. Okay, now, our turkey sandwiches, the recipe for our turkey sandwiches, okay, and these are going to be super boring turkey sandwiches. It takes 2 pieces of bread, all right, 2 pieces of bread, 2 slices of turkey, okay, and 1 slice of cheese. Okay, so there's our recipe to make our sandwiches. Okay, now let's say we've already bought some supplies, and in our supplies we have 46 slices of bread, okay, or pieces of bread, whatever. I'm changing my nomenclature, aren't I? 46 slices of bread. We have 50 slices of turkey, okay, and we have 16 pieces of cheese. Okay, I changed another nomenclature. Got to keep you on your toes. All right. Now, based on this, how many complete turkey sandwiches could I make? Well, assuming that I'm not going to break my bread up or anything silly, okay, that I've got, if I used all of my bread, well, it takes 2 pieces of bread, I could make 23 sandwiches from my bread, right? 23 sandwiches if I used all my bread. If I used all my turkey, I could make 25 sandwiches. So I couldn't make 25 sandwiches because I'd run out of bread for my last 2 sandwiches. And if I used all my cheese, I could make 16 sandwiches. Okay, so the total sandwiches that I could make, okay, is this value right here, this 16 sandwiches. So based on the stock we have now, I could only make 16 sandwiches. And that's really what we're going to be doing in this part, is we are going to be finding the reactant, okay, that we run out of first. And the reactant you run out of first is called the limiting reactant, okay? So the limiting reactant is the reactant that limits the amount of product formed. Okay, so this is the thing that you run out of first, okay? Run out of first. So in the case of our sandwiches, our cheese was our limiting reactant, okay? It was the thing that we ran out of first. Our excess reactants are the substances that are still left because they didn't have enough things to react. Okay, so these are the things, the leftovers, if you will. Okay, all right, the leftovers. Now, so in the case of our restaurant, it was the bread and the turkey. Okay, so how do you know if you have a limiting reactant problem? It's really easy to tell. Okay, all you have to look at is if I give you 2 known values, okay, all right, values of reactants. So if I say in your reactants that you've got 6 grams of this reactant and 10 grams of this reactant, then that's a limiting reactant problem. You have to figure out which one runs out of first. Okay. Here are the steps, not too bad. You're going to take each known of the reactants to the same product, the moles of the same product. Okay, now this is key, all right, of the same product. Can't be different products. You got to pick one product, convert both of them. All right, whichever known makes the least product is the limiting reactant. All right, whichever one makes the least product is the limiting reactant. So in the case of our sandwich situation, we took each of the 3, okay, ingredients, and we converted them to the same product. Right, we converted it to the same product, which was sandwiches, our only product, right? We were only making sandwiches. We converted all 3 to those, and then we figured out which one made the fewest, okay, or the least amount of sandwiches, and that was our limiting. All right. Not too bad. So let's do some practice problems. Silicon dioxide, or quartz, is usually quite unreactive, but reacts readily with hydrogen fluoride according to the following reaction. All right, so silicon dioxide with hydrofluoric acid, silicon tetrafluoride, and water. Okay. Now it says if 2.0 moles of hydrofluoric acid are exposed to 4.5 moles of silicon dioxide, which is the limiting reactant? So it's a limiting reactant because, well, number 1, it asks for the limiting reactant, so that's got to be true. And then number 2, notice that I gave you 2.0 moles of hydrofluoric acid and 4.5 moles of silicon dioxide. That shows you this is the silicon dioxide right here and hydrofluoric acid. We got both of them, all right? So we're just going to convert them both to moles of the same product. And it doesn't matter what we pick, okay, in this case, because it doesn't ask us for a specific value of either of the products. So let's just convert it to silicon tetrafluoride because that's the first one here. Okay, so we're going to take our 2.0 moles of HF and we're going to convert that to moles of silicon fluoride, tetrafluoride, excuse me. All right, so we're going moles to moles. Remember mole ratio. If you're not good at this yet, you should do lots of practice problems. Okay, moles of HF go on the bottom, and moles of silicon tetrafluoride go on the top. All right, it's a 4-to-1 ratio. 4 goes with the HF because that's the coefficient right there, and then 1 goes with the silicon tetrafluoride. Okay, so and that's it because we're in moles of silicon tetrafluoride. So we take 2 divided by 4, we get 0.50 moles of silicon tetrafluoride. All right, so if all of our hydrofluoric acid reacted, that's how many moles of silicon tetrafluoride we'd make. Now we're going to do the same thing with silicon dioxide. So we have 4.5 moles, okay, of SiO2. All right, plug this guy in here. So now we got moles of SiO2 here. We're going to moles of silicon tetrafluoride here. All right. So now we find our coefficients. It's a 1-to-1 ratio this time, so 1 to 1, okay? And so if all of our silicon dioxide reacted, we would make 4.5 moles of silicon tetrafluoride, okay? So that means HF made the fewest, so that is the limiting reactant. Let's just say LR for limiting reactant, okay? Easy peasy. All right, let's do another one. What is the theoretical yield of copper 2 sulfide that can be formed when 80 grams of copper reacts with 25 grams of sulfur? Okay, so this has to be a limiting reactant problem because we're starting with 80 grams of copper, and that's this reactant right here, and 25 grams of sulfur, and that's this reactant right here. We want to know the theoretical yield. Remember, the theoretical yield is the math, how much the math says we can make of this copper 1 sulfide. All right, so we're going to convert both of these to moles of copper sulfide. All right, and we could actually take it a step farther because it says what is the theoretical yield, and remember theoretical yield always means grams. Okay, so we're going to convert this to grams. We might as well just skip a step because we're going to have to do it anyway. All right, so we're going to start with our 80.0 grams of copper. Okay, and we're going to convert that to grams of copper sulfide. All right, so this is a 3-step problem, right? Because we got to go from grams to moles to moles, and then moles to grams. All right, so grams of copper go on the bottom. We're going to moles of copper, all right? And then we're going from moles of copper to moles of copper, or moles of copper sulfide, Cu2S. And then from moles of copper to sulfide to grams of Cu2S. All right. So now we're going to fill in our numbers. All right, so for 1 mole of copper weighs, this periodic table is too small. Copper 63.55, all right, 63.55 grams. Now we're going to use our mole ratios. So moles of copper, that's a 2, that's the coefficient in front of the copper, and copper sulfide is 1. All right, and then we're going to go from moles of copper 2 sulfide to grams of copper 2 sulfide. So we're going to need to find the molar mass of copper 2 sulfide. So we got 2 coppers, 1 sulfur. Add those guys up. So we have 2 times 63.55 plus 32.07 for our sulfur. So 2 times 63.55 plus 32.07, 159.17. All right, so we'll stick that guy up here, 159.17. All right, so now we're just going to do the math here. So 80 divided by 63.55 divided by 2 times 159.17. All right, and we get 100 grams even. So we got 3 sig figs, so it'll just be 100, and don't forget the decimal because we need to make sure that people know it's 3 sig figs. So this would be 100 grams of copper 1 sulfide. All right, so if all 80 grams of copper react, this is how much copper sulfide we'd make. But we don't know, sulfur might make less than that, so we need to double check the sulfur. So we're going to have 25.0 grams of sulfur. All right, it's a lot of the same steps. Okay, so it's going to be a 3-step problem because we're starting with grams. We need to end with grams. All right. So we're going to put grams of sulfur in the bottom, moles of sulfur in the top. For every 1 mole, each mole weighs 32.07 grams. All right. We're going to put moles of sulfur at the top, moles of Cu2S, all right? And so this is a 1-to-1 ratio, and we know that because the coefficients are both 1-to-1. And then moles of Cu2S to grams of Cu2S, so for every 1 mole, and then it's the same molar mass, so 159.17. All right, so now we take our 25 divided by 32.07 times 1 divided by 1 times 159.17, and we make 124 grams. 124 grams of Cu2S. All right, so that means this is the answer. That is our theoretical yield, okay? Because we can't make more than 100 grams, because anything more than this 100, we'd run out of copper, and then we really couldn't make copper sulfide because we don't have enough copper. All right, so anyway, so that's how you do these problems, limiting reactant problems, and that's the end of Unit 8. Do lots of practice problems. It's a short unit, so that's nice. All right, do lots of practice problems. Let me know if you have any questions, and I'll see you on the flip side.